Yeah, Dr. Toimur Khan sir. Hello.
Hi, sir. Good afternoon.
Good afternoon. So,
Welcome and
yeah, can
welcome
we
to
start now?
yes,
Yeah.
yes, and welcome to the third and last session of the day.
Yeah,
Okay.
yeah. Thank you. I think so. No other participants have joined till now.
No, no,
It's
no.
already three.
Participants are there in YouTube.
Acha, acha. All the participants are attending in
Yes,
YouTube.
yes, yes, yes.
Oh,
They
okay,
are
okay.
they are using separate platform.
Acha, acha, acha. Okay,
Okay,
okay.
it's 3 o'clock. We can start now.
Hmm.
Okay. Uh, Very good afternoon, everyone. I would now like to welcome the third and last speaker of today's session, Dr. Kaushik Guha from NIT Silchar. Dr. Guha received his BTech degree in Electronics and Communication Engineering in 2005 from Techno India, Calcutta under West Bengal University of Technology, India, and his MTech degree in Electronics and Communication Engineering with a specialization in RF and microwave in 2007 from Bardhaman University, West Bengal, India, followed by PhD from NIT Silchar in 2016 on design and modeling of RF MEMS shunt switch. Currently, he is assistant professor in electronics and communication engineering department here at NIT Silchar since 2010. Dr. Guha worked as a lecturer in the department of ECE at Haldia Institute of Technology, West Bengal, India during August 2007 to June 2010 and served as visiting faculty of NIT Mizoram from 2012 to 2014. With this, I invite Dr. Guha to start the talk.
Yeah, thank you, Dr. Khan, for giving me the another opportunity. I think this is the second time I'll be delivering my talk on your program, and this is the not your program actually. That rather I can say this is our program because I am also part of this program. Okay, and I belong to this NIT Silchar and the Department of ECE. So okay, so let us share my screen and switch off my video to save the bandwidth. Yeah, so my screen is visible.
Yes, sir. Your screen is
Okay,
visible.
okay, thank
You
you.
can
So today actually, uh, so the theme of the actually workshop, it is very pertinent and relevant in today's modern times and modern era. That is the smart city. So, and I'll be talking on the topic of green and self-powered Internet of Things. This is the first day. I think the two speakers have already talked about some different issues and topics of the smart city applications. And I hope that in the rest of the 4 days, also the many dignitaries and distinguished speakers will talk some different things, some other research topics. So I have chosen this topic because I work on the areas of energy harvesting, so that's why I have taken this topic. So this will be my brief content of my talk. So I will talk on these issues. So first actually I will talk on the smart cities and the applications of the IoT in the smart city, the use of the Internet of Things and sensor nodes in the smart city, and then the why the energy is a crunch nowadays. What is the intelligent way to harvest our available energy that is present in our environment, and then of course then I will also briefly touch upon our research areas, what we have started. Actually we have started a very new on this topic, the energy harvesting using the MEMS technologies. So I will touch upon also these some research aspects on this issue. So when we talk about the smart city, then we can say that all around the world, urbanization is a growing need and growing trend today. As more and more people get together, smart systems and their integration need to be developed not only to provide the services that people need, but also to do some efficiently with minimum impact on the environment. So we can say that the efficient ICT, that means information and communication technology, one part of which is the Internet of Things is a common dominator. So it is tying together services, residency, mobility, infrastructure, and energy. So in everything. So the smart city, if we can say definition, that means the cities. So it is a good amalgamation of the technology. That means the information, communication, and technology, and our living life, living culture of the people, of the city dwellers. So if we integrate these two things, then actually we can develop this type of concept of smart city. In the picture we can see the smart city means that everything has to be smart, like from car parking to the smart mobility, the smart metering, smart energy, then smart building. That means in the building and houses will consist of the smart temperature controlling, then the water controlling, and all the other aspects. The smart energy, then smart retailing, the smart product management, the smart working. So everything it comes actually in a smart way, but obviously we have to take the help of the technology, and the technology is the information and communication technology. So, but also in the backbone of this technology and this smart city, what actually we have seen, the most important the contributor is the Internet of Things. So what is that IoT? IoT, we know that it is an ecosystem of connected physical objects that are accessible through the internet. So it has mainly the four actually functions. It has to collect from the environment, from the sources, from the necessary platform, and then it will communicate with each other, and then it will analyze the information and data, and then it will do some act. So if we combine all these four parameters, the four attributes, then we can successfully design the Internet of Things. And also in the Internet of Things, the wireless sensor network also plays a great role, because it is a collection of sensing devices, the sensor nodes. It can communicate wirelessly. So obviously in a smart city concept, when everything has to be communicated with each other, there is a sensor nodes will be deployed, billion and million amount of sensor nodes, and we have to communicate. We have to monitor all these communications between the nodes. So the wireless sensor node network actually will play the game here. So, and it is a network of many tiny disposable low power devices called the sensor nodes. So it consists of sensing, computing, communication, and actuation, and the power components. So obviously the power components and powering the sensor node is an issue, because we have seen so far that people have been using the battery technology to power up the sensor nodes, but obviously there is some kind of the hazardous problem. Obviously I will show you what are actually the problems in this type of existing technology to power up the sensor nodes. So the wireless sensor node actually basically consists of tens to thousands of such a nodes that will be deployed in like this. So in this is the wireless IoT wireless sensor map. We can see there is a different module. We can see there is an energy storage module is there, RF module is there, sensing modeling is there. In sensing modeling, there are lots of sensors. There are accelerometers, magnetometers, gyroscopes, proximity sensors, light sensors, pressure sensors, humidity sensors. So nowadays everything can be sensed. And also after the sensing, obviously the power management also is one of the issue, because you have to power up the electronic sensor nodes, because otherwise if you cannot power up properly and efficiently, so the I think so our electronic circuits and all the nodes actually will be totally silent mode, so we cannot make use of this. So the powering and power management, the maintenance of proper power flow is also a very important issue in this IoT. So applications of the Internet of Things, we can see not only in smart home, smart city. Apart from these, we can see some building automation, realistics. Actually, this is actually all the parts. Actually, this is the separate part of the smart city applications. Okay, if we combine all these application, then we can make a smart city. In the smart city should have the smart environment, the industrial also mechanism should be smart, consumer and home automation should be there, healthcare and life science, okay, of people, that should be a smart healthcare. So it is a combination of smart living, smart health, then smart habitat monitoring, smart cities, smart grid. Okay, so everything is going to be the smart. So obviously, then smart house is one of the main ingredient of the smart city application, because in a smart city, also all the houses should also be the smart. So in a smart house means, we mean to say, in a house that we can see the weather sensor, the house should have the smart light, some kind of door sensing mechanism, motion sensing mechanism, vibration sensing, smart gateway, okay, the smoke detector, and lots of other things will be embedded into the smart house. So the smart government, smart lighting, smart building, smart health, smart security, mobility, smart connectivity. So these are the ingredients of to become a successful, to make a successful smart city. Now, if we can see some global overview, so in 2015, actually, the smart cities connected 1.1 billion connected things to the internet, and this number will climb to 3 billion in 2025, according to some study. So many smart city projects around the world use the integrated information and communication technology that actually we are talking about now, to improve its efficiency, manage its complexity, and also the enhance citizens' quality of life, leading to long-term improvement in city operations. So if you can see the global shipments of the interconnected devices using smart cities, then we can see in the graph, that the picture, that there are several components also, whether we can see the big investments uh, in that devices, like in every sector, like healthcare, safety and security, physical infrastructure, energy and resource efficiency, mobility and transport. So and the trend is ever increasing. In 2025 also we can see how the trend is increasing. So obviously it proves that how the smart cities are yeah, is a boom, kind of anything in today's world, in modern research paradigm. So why the people are working towards the smart city, why government are most worried about to make the smart cities in his country. So obviously there is some kind of good outcome, okay, we'll be getting out of that. Just here you can see one, I have just given one example how the smart city will be looking like. So this is one of the actually picture of a smart city. It is the Pittsburgh in South Africa. Also this it is actually they announced as a smart city kind of thing. We can see in this their smart building management, then the distributed renewable integration, smart traffic lighting system, wireless vehicle charging, the smart parking meters and garages, road sensors are there. So this is just one of the glimpse of the how the smart city, how the road will be like that, how the lighting system will be like that, how the traffic systems will be there. So everywhere we need the sensors, everywhere we need the IoT sensor nodes. So obviously the sensor nodes, and you have to work towards the sensor nodes to design a better sensor nodes, to reduce the power consumption of the sensor nodes, to use the energy scavenging in an intelligent way to power up the sensor nodes. But there are some other challenges also, like the standards needed for more interoperability between the devices to enable smart cities and IoT. In terms of power management and creation still remain relatively unsolved challenges, because the actually when we scavenge energy from outside environment, then also we have seen that it is a very small amount of energy. So obviously people are working towards that to increase the level of the energy standards. The security also another concern, because it is a critical at the sensor node level to ensure secure end-to-end solution, because we have to think also the security also, because when you welcome all this type of technology, information and communication technology, all the sensor nodes, but at the same time we have to be very cautious about the privacy and security also. So these are the some of the summary of the technologies where IoTs actually are used. So in now in the coming years, in all the sectors, I think almost all the sectors we are going to see the application of IoT. It may be transportation, it may be consumer and home automation, it will be healthcare, it will be building automation, industrial, environment, public safety, retail and logistic. In every sector we are going to see always there is a IoT and sensor nodes are deployed, and it is always communicating with each other. Then what are the design challenges in the conventional wireless sensor networks? Though the sensor node has the limited energy supply, because it is very hard to replace in the existing technology. If it is battery operated technology, so it is very hard to replace or recharge the nodes, the batteries once deployed, due to because number of nodes in network is very high. It may be deployed in large area and difficult locations like hill stations, hostile environments, forest, inside walls. So it is very difficult to replace the battery there. The nodes are ad hoc basis. It is deployed and distributed. There no human intervention to interrupt nodes operations. So the wireless sensor node performance highly dependent on energy supply, because higher performance demands more energy supply. So bottleneck of conventional WSN is the energy. So energy is actually one of the bottleneck. So that's why lots of people are putting more thrust to this sector, energy. So how to use the energy efficiently, how to reduce the power consumption, how to scavenge or harvest the energy from other available sources like the ambient vibration, maybe the solar, sun ray, maybe the wind, or it may be the other kind of energy sources. Some correlated or uncorrelated sources are always there, okay, around us. So energy is ever present, but we have to use it efficiently, intelligently. We have to harvest that energy. We have to produce the power and voltage to power up the sensor nodes. So now the question is, why the green IoT? Because in numerous advantages of IoT are enriching our society, but Internet of Things also consumes energy. It embraces the toxic pollution and e-waste like our battery actually, which causes new stress on the environments and the smart world. Because so the smart world means you have to also think of your carbon footprint. So the smart world and smart city must have very low and minimum carbon footprint. So you have to design in such a way that the energy consumption and the power consumption will be very, very low. So it will actually, so this is one of the major challenges. So in order to increase the benefits and reduce the harm of the IoT, there is an increasing desire to move toward the green IoT. So what is the green IoT? Green IoT is seen as the future of the Internet of Things, that is environment friendly, where the machines, communications, sensors, clouds and internet are alongside energy efficient and reducing the carbon emission. So it has a three main part. The green IoT, it should have, one is the energy efficient procedure in IoT, then it should reduce the greenhouse effect, and also it must reduce the carbon emission. So these three actually the main part of the green IoT. And in our upcoming IoT technology, in green IoT, we have to implement these three techniques. So the three, it is the energy consumption, so that it will provide the sustainability, and it will make our world smart but safe. So the smart city and smart world, but also the city should be very, very safe. Your home should be very, very safe. So, and also our world, okay, our environment should be also very, very safe. So these are the main three actually, the important pillar we can say towards the green IoT, the smart and safe world, and sustainability, and the reduce of energy consumption. So the how can we make it possible, the IoT? Obviously using this, some of the ways are that the green design, then you have to also the production should be the green, that means there should not be any energy waste type of thing. So to reducing the carbon footprint, then green utilizations and green disposal. So all are things that it should be the green. So green RFID means radio frequency network, green CC means computer clouding, green WSN means wireless sensor networks, and that will not use the battery as a power source, obviously using the energy harvesting as a technique to power up. Then green machine to machine communication, and then data center. So this is actually the ICT technology. In the ICT technology, these are the technology verticals, where these actually the 6 technology verticals are important to make any ICT or information and communication technologies. So if we see the world statistics, then we can see that it is predicted that there will be 50 billion of permanently connected things by 2020. I think in the last year already it has surpassed. Then some years later, it will be 10 trillion connected sensors. So the question is how these billions of communicating devices and sensors be powered without harming the environment. So the viable solution is the green and self-powered Internet of Things. So now it is the question of energy harvesting. So actually, what is called the energy harvesting? It is the process of capturing ambient energy and storing as electricity. So the energy harvesters enable self-powered electronic devices for various wireless electronic applications to replace limited lifetime and bulk batteries. So the flow of the energy harvesting system is like that. First, so it is the energy harvester will harvest the energy. Then power conditioning technique or power conditioning circuits will be there to monitor the power, to monitor the flow from input to output. Then the energy storage, obviously you have to store the energy for future use. Then proper energy management. So energy management is also one of the big issue, because you have to flow your energy to different parts, okay, and effectively, and you have to utilize properly the available energy. And then after that, it will be go to the WSN load, that means the wireless sensor networks. So the wireless sensor node structure, we can see it is a sensor, combination of sensors, some electronic circuits, some memory will be there, and the communication unit. So as a whole, it will make a wireless sensor nodes. And powering this wireless sensor node is nothing by none other than this, that is the energy harvesting device. So there are many energy harvesting technologies existing in the present world, that we can see. Maybe the light energy harvesting, that means photovoltaic. Electromagnetic energy harvesting technology is already there. Then thermal energy means thermoelectric effect, pyroelectric effect. Kinetic energy harvesting, then vibration energy harvesting, okay, then piezoelectric energy harvesting, electromagnetic energy harvesting, triboelectric, electrostatic. So lots of technologies are already there actually, because and also lots of people are working towards the different energy harvesting systems and technologies. So what is the green and self-powered Internet of Things? So it is the powering the IoT devices is a major challenge, because the conventional batteries has some disadvantages. What are the demerits? Like it is bulky, it has the limited lifetime, some deployment issues, because in hostile environment, in forest or in hilly region, we cannot go and replace. Then environmental concerns. So in green IoT applications, devices need to be powered in a self-sufficient manner, okay, and sustainable manner. So energy harvesting will enable a self-powered electronic devices for various wireless electronic applications. So now we can see in the right hand side the figure, that is battery versus self-powered. Okay, so battery, if you see the battery, so the energy stored in IoT device using the battery, it will decrease, okay, over a certain period of time. Suppose after 1 year it will go away, and then there is no other way to other than the replacing of the battery. But in the self-powered technology, you can see that it is already it is always over the year also, it will sustain, it will continue like that. So it is energy harvesting techniques harvest energy from different energy sources in the environment. So this is the wireless sensor node anatomy. We can see that so there is a different parts, that power conditioning, the energy storage, the Then the MEMS sensors are also playing a role actually here. So we will also talk about the technology, how the MEMS technology can be the efficient to build this harvesting, energy harvesting devices. So wireless sensor nodes are designed to operate in a very low duty cycle. So the sensor node is put to the sleep mode most of the time, and it is activated to perform sensing and communication when needed, to reduce the standby power. Modern power consumption in active mode and very low power consumption while in sleep mode. So what are the advantages? Means recharge batteries are similar in sensor nodes using energy harvesting. Prolong wireless sensor node operational lifetime or even infinite lifespan. Growing interest from academia, military and industry. Then reduces installation and operating cost, system reliability enhancement. So there are a lot of advantages of this energy harvesting technology that have already been proved, and lots of people are also talking about that. So to implement the energy harvesting technology to powering the wireless sensor nodes. But when we talk talk about the energy harvesting, now the question generally comes in the mind, at which scale? So what is the amount of harvested power and what is the amount of harvested energy, okay, that we can say. So basically there are three type of production actually we can say. The one is the mega scale, that is the large scale energy production for electrical grid, okay, like the harvested power density in the range of megawatt per centimeter cube. Just below that, we can talk about the meso scale, like the large scale power devices, but not at the mega scale. So power density in the range of watt per centimeter cube. And also below that level, very small power level, it is called the micro level or micro scale. That is the MEMS or name scale for ultra low power electronics such as wireless sensor nodes and wearable electronics. So here the power density in the range of microwatt per centimeter cube. So now micro scale actually has gained a lot of interest because meso scale and mega scale is already there in for long years. Okay, this technology has been put on use, but the micro scale actually how to, so using a bit small devices, okay, how to generate the power, how to gear up the power, boost the energy. So that is also very, very interesting research topic, and here actually MEMS plays a very good role in developing this micro scale energy harvester. So there are different kind of energy sources, ambient energy sources. We can see that like light or photovoltaic. The harvested power range, it is indoor, means it is 10 microwatt per centimeter square, or if outdoor means 10 milliwatt per centimeter square. So advantages may be high conversion efficiency, mature, scalable, but challenges are also there. Small surface area for wide input source. Then thermal energy is also there, harvested power in the range of microwatt per centimeter square, or in industry it is milliwatt per centimeter square. So the challenges are also low temperature gradient, low output. Then RF also harvested, RF energy harvesting technology is also there, like it can harvest from GSM or Wi-Fi signals, okay, and the harvested power may be 0.1 microwatt per centimeter square. So it is a very widely available, cost effective, but the coupling and rectification is an issue, low power density. So in addition to this, there are vibration also are that is our the available energy sources around us in the environment. So it can be of three type of energy transaction mechanism that can harvest energy from vibration sources. Like it can be electrostatic in nature. It is the harvested power in the range of microwatt to 0.1 microwatt to 10 microwatt. So it is scalable, compatible with MEMS technology. But one disadvantage is that here external voltage source is required. Then it may be electromagnetic transduction. That means where the harvested power in the range of same the 0.1 to 10 microwatt. But the advantage, no voltage source required. It is also reliable, but difficulty in integration of magnet, low out, because magnet is a bulky thing. Electromagnetic, you require the magnet. So magnetic integration, magnetic interaction is also one of the issue. Then piezoelectric is also there. It is the energy harvested power in the range of higher than the electromagnetic and electrostatic. It is very good, compatible with MEMS, high output, but the one of the major challenges is that decreased coupling and brittleness. So the vibration actually here we can see provides maximum advantage if we compare with the other harvesting sources. So that's why people are actually very much interested to look forward this technology and working on the vibration energy harvester. So the power consumption, if we see the various applications and power densities for various energy sources, so we can see that so in the range of milliwatt to microwatt actually. So if we can generate the power of milliwatt to microwatt, then actually we can power up the sensor nodes, and these sensor nodes will be required to develop your smart city or smart world application. So you have to generate a power that should be range from milliwatt to microwatt. That is enough. So that's why actually then we can take as a micro scale energy harvesting method or technology, so as a point of research or the point of study, because it can solve the purpose. So there are other type of energy harvesting system, that is thermoelectric energy harvesting. Here we can use the Seebeck effect, okay, to generate the power, and then it is the efficiency is limited by the Carnot cycle efficiency. So one of the disadvantages is that. Then the RF energy harvesting, just I told you, this is another method to harvest the energy from GSM and Wi-Fi signal. It is also there. Then photovoltaic harvesting, very popular. The solar cell, from the solar sun ray, we can harvest the energy. The efficiency also can. Also, lot of work actually has been going on the solar cell or the harvesting from photovoltaic technology also. So it is one of the also very interesting work. Then also, so I will mainly focus on this vibration energy harvesting. So the vibration energy harvesting, basically it is a scavenging of waste kinetic energy due to some natural or man-made activity from the surrounding environment and converting it to usable electrical energy. So if the frequency, maybe the source of frequency, vibration, actually the frequency of vibration maybe 0 to 100 hertz, very low vibration means. Then acceleration also, it ranges normally 0.2 to 5 meter per second squares. So that power we can generate, like from human motion, we can generate 4 microwatt per centimeter squares, and from machine it will be very high, 100 microwatt per centimeter square. So in industrial application also there is a good scope in this of the vibration energy harvesting system to harvest the energy. So now we'll be talking about the MEMS technology, because why the MEMS is a good choice to implement this vibration energy harvester. So we know what is the MEMS. MEMS is the micro electromechanical system. It is the beauty of a system that perform both electrical and mechanical functions with the components in micrometer range. Okay, so in a small range that we can develop a good device. Okay, and that devices can help you a lot in developing the energy harvester. So basically the range of the MEMS devices is the range of between this 1 micrometer to 1 millimeter. So there are three following factors actually are there in the MEMS. One is sensors. The sensors are also will act as an input. So the sensors actually will senses the information by measuring some mechanical, thermal, or biological signals from the environment, and then after sensing of that, so the microelectronic ICs will be there. So it will act as the decision-making part of the system by processing that signal and sensed signal given by the sensor. And then third, obviously the actuators will come into play. So the work of the actuator, it will help the system to respond by moving, pumping, or filtering, or somehow controlling the surrounding environment to achieve its purpose. So if we successfully design and integrate all these three following factors, then obviously we can develop a successful and good novel MEMS devices. So where we can find memes, we can find memes in computer printers nowadays also. It is a very vibrant example, a very live example that computer printers inject printed using the memes technology. Then automobiles, airbag sensors, projectors, cell phones, the lab on chip, microfluidics, the optical devices, and lots of other things we can see. So what are the main actually the reasons why we should actually make a very tiny size devices? What is the reason? The reason is basically a very fundamental reason, that is smaller devices require less material to make up. So obviously the energy is also actually is limited in our art, but also the material or resources are also going to be limited in our art. So you have to be very cautious also from nowadays, okay, from today, that we have to use a very less material, okay, for the design. We should not waste the material. The smaller devices require less energy to run. Then the redundancy can also one of the factor, because if your devices will be smaller and smaller, then you can make use of multiple times, okay, rather than using a single time. Because in some kind of application like our space application, navigational application, so you cannot go and repair your sensor and devices when it becomes malfunctioning. So you have to, if you use the redundant array of the sensors in space application, then obviously if one of the sensor is going out of the work, okay, the other sensors will work, and also your communication will not be breaking down. So the micro devices are also inexpensive because the material is less. Obviously material cost will be low, and also it can be fabricated in a batch process like our IC fabrication process technology. So these are the reasons for this choosing the small size devices. If we talk about the materials for MEMS, so there is a wide scope in choosing the materials, okay, rather than our IC technology, because in MEMS we can choose the polymers, we can take the ceramic materials, we can take the semiconductor materials, metals, composite materials, everything. So there is a wide scope in choosing the substrate like plastic, glass, ceramic. Then thin films also may be different type. Then packaging also, different type of packaging, different type of metals and semiconductors are used. So there's a lots of the availability of the material. So you can pick up anyone and you can develop your device. As a function control system terminology, we can say MEMS is a technology that can enable the miniaturization and lower cost manufacturing of the existing product. Because in earlier days, the all the sensors like pressure sensor, tilt sensor, microphone are there, but the sizes are bigger. But if you actually see in the right hand side, these pressure sensors are coming in a more compressed way, in a more small packaged, okay, form. So the MEMS can act as a transfer function between these earlier days, okay, early days sensors versus the modern day sensors. So MEMS will act as a is acting as a transfer function, like that we can say. So what are the manufacturing process also? So the MEMS design, first you have to design your MEMS devices. Then after simulation and everything, okay, so yeah, you can go for fabrication. Then after fabrication, we can go for packaging, and then after packaging, obviously the testing. So these are the four phases, very normal phases actually of our MEMS fabrication, like the IC fabrication for technology also. The fabrication process are also similar, okay, with our IC. Like here we can see the photolithography is also there, ion implantation, diffusion, chemical vapor deposition, sputtering, epitaxial layer deposition, etching. So this is also there in the MEMS also. But in addition to this, actually in MEMS means there, it is called the micro machining techniques. So what is the micro machining techniques? It is basically the two type micro machining. One is the bulk micro machining, that is whenever if you actually the cutting the bulk of the material of your or the semiconductor substrate, okay, or to develop something, that is called the bulk micro machining, where bulk of the substrate is interrupted, okay, or the interrupted. But in contrary, the surface micromachining means your bulk of the silicon substrate will not be interrupted. It will be remain as it is, but you can develop your devices or architecture on the top of the substrate. This is called the surface micromachining. And also there are other sophisticated micromachining process that is called Liga. Here you can fabricate or develop very sophisticated, very high resolution, high aspect ratio structures. Just for giving for an example of a bulk micromachining, just one diaphragm actually of a pressure sensor, how it will be fabricated. So if we, so this is the first step. We can say take a silicon wafer as a substrate, then we can grow the SiO2 layer. Then after that, you will grow the spin the photoresist layer by spin coating method like this. Then you will align the mask for lithography. Then you will expose the UV ray. So now it will be unexposed region will be developed, and this unexposed photoresist will be removed by the developer solution. And also then you can etch the SiO2 layer with the HFL solution like that. And then after that, we will also remove the unexposed part also by this. And then you can also etch the substrate, the silicon substrate, okay, with KOH solution like that. So this is the bulk micromachining, where substrate or bulk part of the substrate actually is being cut away. So this is the bulk micromachining. So in bulk micromachining, we can see generally the two type of etchings. One is the isotropic etching, that the etching profile is uniform. Here we can see in vertical direction and horizontal direction, here etching is rate is uniform, so that it can generate a very regular kind of geometry. And another is an anisotropic etching, where the etching rate is not uniform in all directions. So in maybe here in this case, the vertical direction, the etching rate is more rather than the in lateral dimension. So and the lateral direction. So that's why it will make some kind of slope-like of structures. Okay, this is called the anisotropic etching. So some of the figures that is coming out of the anisotropic etching technology like that. So some complicated structures like V groups, nodules, pyramidal structures can be actually fabricated using the anisotropic method. So in contrary with the bulk micromachining, the surface micromachining example, just now I want to create one cantilever using that. So I have taken the substrate again, and then I have deposited the polyimide layer. So the green band is that. So now you can etch part of the layer like this. So we are etching out, and then again you will deposit some aluminum layer like this. And now we can also remove this layer, green layer. It is called the sacrificial layer. This process is called the releasing process. So after releasing, it will look like a freestanding architecture. So this freestanding beam is called the cantilever. In MEMS is very, very popular beam actually in the MEMS design. So the surface micromachining means, so in a layman point of view, we can say, so it is a kind of green flat plate. It is a substrate, and on the top of the substrate, your kids, our kids, okay, will put some of the toys on that, and he can build some type of good kind of cities or good kind of structure, kind of that. So this is called the surface micromachining, where the surface of the silicon substrate that will remain as it is, will not interrupt it, but we can grow our design or our layer on the top of this. This is the surface micromachining technology. So again, the application of MEMS, we can see here a lot of application in bio area, also in bio-MEMS, like in doctors, in medical, in healthcare sectors. Okay, lots of nowadays people are working on this. In industry areas like defense industry, we can see MEMS, aerospace, automotive, biotechnology, telecommunication, analytical chemistry, information technology. See, everywhere, all around the world, we can see the MEMS technologies. So, but in biology, we can see blast sensors lab on chip, the very, very interesting and booming field. Okay, nowadays the people are working. Then optical MEMS means MOEMS, the projector scanners. Then inertial measurement also we can see accelerometers, gyroscope, pressure measurement also we can see. Then radio frequency MEMS, very important nowadays, because it is very relevant in our coming 5G technology, because most of the 5G technology, the parameters, the background, okay, are actually depending on the RF MEMS based architecture of the devices and components. So, and lots of other technologies are also there. And then apart from the sensing, if we can talk about the actuation principle of the MEMS, then we can see there are 4 very basic actuation principles are there. One is the electrostatic actuations. It is very simple, low power, fast response. Then the piezoresistive actuation, maybe, so it will be based on the well-known phenomena that changes in resistance with strain. Then thermal actuation are also there, so it is based on the changes in temperature profile, temperature gradient. And then last but not the least, very interestingly, piezoelectric actuation. So it is also one of the very interesting phenomena, that is changing electric voltage or polarization with the stress. So here we can develop our automatic voltage, okay, just by pressing the devices. So it can generate some own output power and voltage. So no need to apply the separate voltage sources to make this piezoelectric based MEMS devices. So there are some fabrication of the energy harvesters. We can see the thermal, the thin film thermoelectric generators, TEG. It can be fabricated using micro machine technologies. Then piezoelectric vibration energy harvester or electromagnetic. This part can also be done with MEMS technologies, and that are already existing in the reported literature. So there are some steps that we can see to fabricate the MEMS piezoelectric energy harvester. So it is just the same steps that actually I just discussed now. So the growing some layer, then sputtering, then etching, okay, then chemical vapor deposition for some deposition of some oxide, then lithography process, then the reactive ion etching. And so these are the same. So using the MEMS procedure, we can easily develop this type of energy harvesting products and devices. So these are some examples of, you can see the MEMS piezoelectric energy harvesters. So here the frequency ranges 31 to 232 hertz. So it is a wide range of frequencies, the resonant frequency. Then also we can see the 3D vibration driven electromagnetic energy harvester are also present nowadays. Then MEMS rotary comb electrostatic harvester is also there. So mainly actually I am focusing on the vibration energy harvesting because it has a wide scope, and the power generation also can be, the scale of the power can also be maximized, okay, because it can generate up to 100 microwatt from the machine. So that's why actually it took me actually to grow the interest to work on this vibration energy harvesting, and it is also ever present, okay, in the ambience. So like one of the example of vibration energy harvesting, like staircase vibration from running up and down, we can easily generate the good amount of energy using this. So the good research work in University of California, the group, they are working on this. So harvesting energy from a wooden staircase to power the temperature sensor. Then motion or kinetic, it captures the kinetic energy of normal everyday motion. Okay, it is helping solving the military's high pin mobile power crisis, transforming the way mobile devices are powered. Then the battery-less remote controller or light switching application. So we can see the vibration energy harvester. So what are the now the question is, what are the present challenges and limitation vibration energy harvester? Because the challenges is ambient vibration is very low and broad range of frequency that I told you, it is very low. The ambient vibration is below the range of 100 hertz also, so very difficult to pick up that. The linear vibration energy harvester works only for a resonant frequency. Suppose so linear vibration energy harvester, that it only takes only one resonant frequency. If your resonance actually, if your device just shifted slightly, out of the resonant frequency, okay, then actually your vibrator energy harvester cannot pick up that energy, and then your power generation is very, very small. So very narrow resonance bandwidth, harvested power density is very low. So these are the challenges and limitations in our existing vibration energy harvester. So what should have the ideal VH? The ideal VH should consist of the capability of harvesting on a broad band of frequencies, and not only at the resonant frequency. So apart from the resonant frequency, it should take, or it should cover the entire frequency range. Then it should be capable of harvesting low frequency, few hertz, because in normal vibration in our environment is very, very low. It may be 50 hertz, maybe okay below than that, also 10 hertz, 20 hertz. But so your ideal VH should also capture that very low frequency. Otherwise, you cannot harvest the low frequency part. Always you have to do for high frequency energy harvesting. Then high output power density, it obviously it must have the high output power, automatic tuning provision. So these are the some properties that should be there inbuilt in the ideal VEH, or vibration energy harvester. So if we can see some comparative analysis between all types of vibration energy harvester that we talked about, like electrostatic, electromagnetic, and piezoelectric, then there are some advantage and disadvantage of every the technology. Like if you talk about electrostatic, it has some good set of advantages, and also it has some good set of disadvantages. Then electromagnetic also, you can see the advantages are reduced mechanical damping, no separate voltage source required, lower operating frequency. Electromagnetic actually vibration energy harvester can operate very low operating frequency. But the disadvantage is that it is very bulky in size, because you have to use the magnet or coil, complicate to integrate with MEMS technology, and output voltage power, or output power density is very low. But if you talk about the piezoelectric, then it has a good advantage on the high output voltage it can generate. It has also no separate voltage source, it is not required. It can generate high power density. It is compatible, very good compatible with the MEMS technology. But similarly, the disadvantage is the same time, it takes the higher operating frequency. That is the one of the major drawback of the piezoelectric energy harvester, that it operates always high operating frequency. So that means, so not a single type of energy or transduction mechanism is not enough, okay, to cover up the entire band of frequency of the vibration. So obviously you have to develop some novel or some kind of hybrid techniques also, where we can combine electrostatic versus electromagnetic, and also piezoelectric and electromagnetic, that can cover a good range of frequency, as well as it can also deliver a good amount of power. So what are the technology to broaden the bandwidth? There are many technologies that we can broaden actually the bandwidth, because one of the technologies is resonance frequency tuning. It can be mechanically, magnetically, or electronically. Then frequency up conversion technique is also there in the reported literature. Lots of actually reports has been published on this. Then nonlinear structure resulting a bistable quadratic oscillator BQD system. So in the figure in right hand side, we can see the comparison between linear, nonlinear monostable, and nonlinear bistable energy harvester. And here we can see that the red line indicates the nonlinear monostable, black is the linear monostable, and the blue one is the nonlinear bistable. So there is the difference in terms of some energy profile, the potential energy profile versus displacement. There is some kind of differences. Then another technique is there, segmentation of electrodes in piezoelectric energy harvester. Also, the nowadays people are also started thinking to implement this technology. And the fifth one is the hybrid energy harvester. So we are working mainly on the 4 and 5, actually these two techniques, to develop our energy harvester, that is using the segmentation method, and also some good hybridized or hybrid energy harvesting mechanism. So this is the basic piezoelectric energy harvesting mechanism we can see. So it is the piezoelectric effect where it can convert mechanical energy into electrical energy due to this piezoelectric effect. So here we can see there is a substrate, and also on top of the substrate there is a piezoelectric layer is deposited. And if you apply some pressure, so this piezoelectric layer will bend, and when it will bend, then the strain will be developed, and due to the strain there will be output voltage will be developed. So it has a high conversion efficiency, but at the same time it is low ductility and toughness. That means so it is brittle type of thing. So what are the limitations in this design? Here it is the linear resonance structure with narrow bandwidth. This is the main drawback of the piezoelectric energy harvester. Non-uniform strain distribution, maximum at fixed end and minimum at free end, because in cantilever structure, so the strain actually, if we see the strain distribution, always the strain is more in the or maximum at the fixed end. Okay, so at this end, but in the free end the strain will be very, very minimum. So there is a non-even distribution of this strain. So due to this non-uniform distribution, so after some cycles of operation, this type of harvester can break, okay, or can rupture. So we have to think of this also. So it is inefficient use of device volume. Then charge cancellation at a higher vibration modes, reducing power generation. In piezoelectric in device that we will see in higher vibration modes, there is the effect of charge cancellations. Okay, so due to the charge cancellation, then the power actually output is low as compared to the other vibration technologies. Resistive load is not practical, so it is an enormous resistive load, so it is a very, very high, so it is not going to be practical. So these are the actually limitation in our present design, where in the piezoelectric vibration energy harvester. So what is the way? So here actually we want to develop some kind of optimal shape of the cantilever based piezoelectric energy harvester. So here actually we are not using the so-called the rectangular shape, because the rectangular shape has some kind of limitation in strain distribution. But if we shift from our structure from rectangular to trapezoidal or triangular, then from the literature it is proved that, okay, here you can see that how this strain distribution will be uniform in triangular vibrators or the trapezoidal vibrators, okay, rather than the rectangular vibrators. So if we see the comparison between these three type of vibrators, then we can see the voltage output also is very, very high in triangular vibrators. So the strain and voltage of triangular vibrator is more than those of a rectangular and trapezoidal vibrator. So trapezoidal vibrator piezoelectric vibrator is the best choice for low frequency, because also at the same time you have to think of frequency. If you are interested to capture the low frequency, then the blue can be the best solution, because it is lying in the middle of the rectangular and also the triangular part. In triangular vibrator is very good in power output voltage, but it also works on the high frequency range. So this is the one of the way that we have adopted. And the second technique that we are also adopting, that is the segmentation. So the segmentation means, in the right hand side in the picture here we can see how the piezoelectric charge is flowing in the bending of vibration modes, higher modes. So whenever you apply some stress or strain on the piezoelectric beam, so the charges that it will be developed like this way. Okay, so positive, then negative, positive, negative, or in after certain cycle, after certain length, then so it will going to alter. So it will be negative, positive. So it will be in reverse way. So at this point where one positive and negative charges are side by side, we can see it is called the strain node position. Here the charge cancellation occurs. So due to this charge cancellation, obviously it will affect the total voltage or output voltage. So if we segment actually, so if we cut this beam at this strain node position, and if we add all these voltages, okay, from the different parts of the piezoelectric cantilever, and we add up all these segments, then we can also make a very good amount of power. So this technique is called the segmentation of the electrodes. So the segmentation avoids charge cancellation due to covered strain nodes. So optimal segmentation of the piezoelectric material at strain nodes of higher modes of vibration increases the efficiency of the vibration harvester. So this is another technology or technique to increase the power output of the piezoelectric energy harvester. So now actually we have developed this type of architecture where we have adopted the the trapezoidal geometry, not a rectangular geometry, because of the uniform charge the strain distribution, and also at the same time we have also adopted the segmentation method. Okay, and then we have seen there is a improvement in our results, that if we compare the segmented trapezoidal versus non-segmented part and rectangular part, then we can see that our strain distribution is very uniform and good. And also in terms of the voltage, also in segmented trapezoidal electrodes, the voltage generation is also quite high rather than the without segmented piezoelectric energy harvester. So this work actually very recently published in the Journal of Microsystem Technologies on this. So now this is all about the piezoelectric energy harvester part. Now just I am going to talk on this electromagnetic energy harvester. So it is the magnetic energy generator where permanent magnets, we can see, these are used to produce strong magnetic field. So electrical energy is generated from magnetic field using electromagnetic induction method. Okay, so using this electromagnetic induction method, we can generate the electrical energy from the magnetic field. So it is very easy and cheap to design, and scalability issues and low energy density, because they usually require bulky magnets and coils. So this is one of the disadvantages of the electromagnetic counterpart. Wideband electromagnetic energy harvester. So this is one of the very good example of the Tyndall actually has developed a very renowned, very popular wideband electromagnetic energy harvester and reported in the Nature, actually the journal. So they actually their group actually have shown that the comparison between this kind of energy profiles, where they have proposed a very new concept, that is quartic potential method, that is called BQT, bistable quartic potential technology method. So in their new technology, so they actually shown that so they are getting very high power from the electromagnetic energy harvester using that design. So bistable quartic potential profile, it will enhance the performance across the vibrational spectrum. So recently, actually, we have tied up with some international project with Tyndall, and we are working toward this. Actually, we are aiming to also develop a good the hybrid piezoelectric and electromagnetic energy harvester. Here we are making the use of both. Piezoelectric is very good for MEMS technology. Piezoelectric is very good for high power density, high power generation. Okay, but the disadvantage is that it captures high frequency, but at the same time electromagnetic has the good advantages on it works on low frequency. Okay, so if we combine these, both the harvester or both the transduction method, so we can say in a single harvester, then also we are aiming to develop a very good results and very good output power. So our new devices will be very reliable. So it can capture wide frequency range also. So the strain distribution profile will also be very good. So almost all the features actually we are expecting, that is the performance will be very good out of this type of devices. So actually here we are actually combining all this technology. We can see we are combining the piezoelectric energy harvesting technology, then we are adopting the segmentation method, then we are adopting the non-uniform geometry like trapezoidal or kind of other geometry, which is not a rectangular one. And after that, we are also aiming to attach or interface one good power management service. So if we capture and if we combine all these four different parts, then actually we can develop a very novel type of self-powered this vibration energy harvester. Is like that. So So if you want to make it more novel, that means I have to then combine this electromagnetic energy harvester with our newly developed the piezoelectric energy harvester, and that will make a complete hybrid vibration energy harvester. So it has the so many components, very good. The performance wise, it will be a low ambient vibration, wider bandwidth, high power, more lifetime, more reliable, and under string safe limit. So these are the very important parameters of any vibration energy harvester. And our application are aiming into industrial machine monitoring using acoustic wave emission. It is range of frequencies 0 to 200 hertz, and also very low vibration. That is the acceleration 0.05 to 0.2 G. Also, it can be used in tracking and tracing of cargoes in automobile. Also, maybe the powering of temperature sensor in HVAC system in a building. So these are also basically application of the smart city or smart house, we can say. So there will be also the challenges also, but also we are working towards that. So we are hopeful that we can design this one. So this will be the design flow actually in the working, that how we are progressing towards like that. So first we have taken the proven technology, that is present technology, rectangular rectangular based piezoelectric energy harvester. Then we have changed the geometry to the trapezoidal. Then we have applying the segmentation method. Then we are increasing the bandwidth, okay, with some magnetic interaction, some other technologies, okay, some other techniques are also there. Then applying the concept of both thin and stretchable arm, okay, like this. And so it is a mixture of so many things. Actually now we are making it as a good hybrid system, where actually we can have the more lifetime, more bandwidth. It can operate also the very low our acceleration mode also, and also it will work for a long time. So the reliability will also be very good. So it will be the complete system. It is not only the energy harvester, but it will also the power management circuit. So it will be the complete system, energy harvesting system. So hybrid energy harvester, why it is the sustainable energy harvesting? Because it is the sustainable green energy harvesting system for their potential using self-powered smart wireless sensor networks. So it uses more than one mechanism or more than one source to generate this electricity. Hybrid energy harvesting system also can be thought of as the hybrid sources, like so that you can also make a single harvester, that where you can take the multiple sources like solar, maybe the thermal energy, or maybe the mechanical energy. If we can combine all these three, and then also we can make a good hybrid energy system. So this is the hybrid in terms of the source. That can be also done, but now actually at this moment we are doing the hybrid in terms of transduction method, like we are hybridizing between the piezoelectric versus electromagnetic transduction, and we want to develop a single house or single system, single package, where both the transduction method can be embedded. Hybrid energy harvester, you can see some examples. Also hybrid energy harvester are also there in our existing, okay, in the modern world, that we can see the lots of people are also working the hybrid solar and thermoelectric generator, hybrid RF and vibration energy harvester, okay, then hybrid acoustic energy harvesting using piezoelectric and electromagnetic. So this is the prototype of hybrid piezoelectric and electromagnetic energy harvester. Here already I have shown this actually. So this is the key features we can see. It's electromagnetic plus piezoelectric transduction mechanism, non-linear electromagnetic vibration energy harvester using magnetic induced bistability. Here actually we have attached one magnets, okay, to control the magnetic forces, okay, some repulsive forces. So to actually, this is one of the method to increase the frequency, also the range of the frequency, the bandwidth. The segmented electrode technology is also implemented, And also we have made one use of the stretchable beam, because once you the more stretches the beam, that means it will develop the more energy. So after energy harvester, okay, the harvesting the energy, you have to store the energy. So there are available options are there. Option one is the traditional rechargeable batteries, but it is very inefficient charging, lots of energy converted to heat. So it is going to be waste. So limited number of charging cycles. Option two is the capacitors are there, efficient energy, but very limited capacity option. Then supercapacitors are there, where it is very small size, high efficiency, but very high capacity. So supercapacitors are also being one of the good research scope or area where a lot of people are working to develop good supercapacitor to store the energy. Then after the energy harvesting, also you have to store, and after storing also, then you have to also manage for your energy flow to the different units. This is called the energy power micro energy management systems. Okay, so the power conversion and the management is generally the core of the modern energy harvesting system. So not only harvesting is the enough, okay, you have to also develop a good interface circuit to interface your energy harvester to the your outside world. So there are different type of power management circuits are also there. So the different technologies are also used to maximize the power flow from input to the output. So these are some available energy harvesting products we can see that is existing in today's world. The cell powered smart street lighting system, then vibration energy from train wheel, then cell powered smart watch, then cell powered wireless switch for lighting and shading. There are so many also. So energy harvesting system in the market, if you can see, the piezoelectric harvester made with ribbons and PZT, that is a biocompatible plastics with an integrated rectifier and rechargeable battery. University of Illinois, actually they are working a lot on this. Then the some of the industry, they are also developing very good devices of the self powered energy harvester, electromagnetic energy harvester like Perpetuum in England. Then we can see the silent sensor, also one of the company in England. They are also developing the silent sensors, highlighting the piezoelectric energy harvesting for tire pressure monitoring devices or tire pressure monitoring applications. Similarly, there are lots of power management circuits are also in the market. They are commercially available, like different company like Texas Instruments. They have developed very good the power interface circuits, power management circuit. Then analog devices are also there. They are the market leader also in developing this type of circuits. So in a conclusion, we can say that in a smart world, that smart devices and sensors request power sources that last lifetime of the devices. But energy harvesting wireless technology provides a solution to power billions of communicating devices and sensors in WSN. So the performance of this energy harvester can be further improved by combining different type of energy harvester in a single device to provide a hybrid redundant power source. Suppose, so we can implement multiple sources like solar, wind, thermal. Suppose if any sources are also not working, or suppose it is not actually providing at a reliable amount of power, so that the other power sources can generate power and then it can also work on this. So nowadays the people are working on the multiple sources energy harvesting system, where multiple sources can be integrated together. And also we have to also look for the good power conversion and management circuit, because it is the core of the energy harvesting system. Now, obviously, the people can ask about what are the best tool in main that we can work on this. So actually, in our lab, we have we have been working on these tools. COMSOL is very good option, or it may be the IntelliSuite, Coventerware. All three main tools are there in my lab. And this is the some introduction of my lab. It is the National MEM Design Center in Electronics and Communication Department department in NIT Silchar. So here actually we are working on the RF main switches, filters, then reconfigurable antennas, energy harvesting systems. Also biomems also we are working on that, some drug delivery systems or some mimicking of some human physiological functions using the MEMS technology. These are my students that they are working on the different topics of the memes and other the memes and also combination of electronics, biomemes, bioelectronics there. Uh, she has defended her thesis. Actually, recently she has done a very good work on the RF meme switches, and she has developed and fabricated also the Nobel switches on the RF meme switches. She is working on the MEMS energy harvesting actually. So we are working together with Tyndall. She is developing the energy harvester. This man, he is working on the. We are trying to actually. We have also very new in this area. We have started very recently to work on the biomems category. So he is working on some trying to mimicking some of the human organs like kidney actually, and then using the MEMS scenario, and we are develop some mathematical models of our human kidney so that it can some of the kidney diseases or some of the characteristics of the kidney or flow of the blood can be simulated okay in the environment in the EC so that it will help our the medical teams and healthcare professional to detect something very easily. Though she is working on developing the MEMS accelerometer for Parkinson detection. He is working on the MEMS tunable substrate integrated waveguide filter for 5G applications. So thanks to my research collaborators that we are working together, okay, to develop good actually and to towards a good and sustainable research in the MEMS field. So these are the men behind this. This includes some doctors also, and these are my international collaborations. And we can see we are tied up with this actually people for different projects or some other activities also. We are also working together. And this is the scope for future students like the future students when those who are interested to work on my group, so they can work on this type of topics like MEMS microfluidics, MEMS switches or RF MEMS, biomems, MEMS energy harvesting, VLSI. Also we work on the analog circuits, digital circuits or optimization systems. So if those who are interested to work on my and my group's work okay on the MEMS field, so they can refer to this research gate profile or in my institute profile also. So there are all the papers are there. So all the papers are available. So those who are interested, you can go to and see our work and recognize our work. So this is so that I end up here. So thank you for your kind attention. Wishing a very happy New Year 2021 to all. And for any query after this session, also you can post a mail to me. So thank you. Thanks a lot.
Thank you. Thank you, Dr. Guha. Now
Thank you.
I was looking the chat box on YouTube link, but there is no such query on your lecture. Everybody has appreciated the talk delivered by you. It is an great
So
achievement.
no, I think so. There can be different way also. Na? There no nobody liked that talk also.
No,
They have no.
no, I think that is not there. And
Yes,
anyway, we are in a stage to conclude that today's session.
yes, yes.
Before that, we are extremely thankful of you for
Thank you.
giving us the opportunity to listen on this emerging area of RF MEMS switch in context of smart city environment. In spite of today's other activities in the department, you have spared time and
Yeah, yeah.
it is more than sufficient for us. With this,
Thank you. Thank you.
thank you, Dr. Goa, once again. And thank you to the participants also for listening all the three sessions with full of energy that I was continuously monitoring on the YouTube channel. With the same energy, hope that you should come tomorrow for the next day or day two session first at 9:30. Till then, bye. Good night. Good evening to all of you. and see you tomorrow morning.
Thank you, sir. Thank you, Khan sir. Okay. Thank
Okay, sir.
you.
Bye.
Thank you, sir. Bye bye.